Alright, hello. So today we're going to work through a concrete example of camera equations. Yeah, let's just get right into it. So we're going to take, wait a second, how can I okay, here we go. So we're going to take a triangle and we're going to have our robot look at this triangle, and then we're going to work our way from the triangle being defined in world coordinates, and we're going to work out where in the image that the robot sees the triangle is supposed to be. Yeah, that's the plan. So let's draw and yeah, I'm just going to be really slow and explicit and like really focus on being overly verbose, and then in the next lecture I think we're going to speed up and just treat all of this as given and not spend time on going into details. Anyway, so here's the situation. So this is the word frame. X, Y, no, this is Z, X, Y, and Z, so Z goes up, and then our triangle, let's say it's going to be at X equals 0, for no particular reason, honestly, and then the camera is going to be at X equals -5, Y equals 0, and Z equals 0, and looking towards the X direction as by convention. So here's the camera at X minus 1, 2, 3, 4, 5, right? So the camera is right here, and then let's say that our triangle is, let's say, at Y equals -2, and then Z equals, yeah, let me just write them slightly different, maybe like X equals 0, Y equals -2, and then Y equals -1, and then the other one is like at Y equals 1, and then Z equals -1, and then the third one, it will be like X equals 0 again, and then maybe Y equals -1, and then Z equals 2. So let's just draw it. So first one, -2, -1. So x0, 1, 2, -1. Here's the point number 1, P1, P1. Then P2, 0, 1, -1, 1, -1. So somewhere around here is our P2, and then our P3. -1, 2, so -1, 1, 2, somewhere around here, right? Something like this. Yeah, nice. Let's just use colors, why not? So this is yellow, and then reds, and then I don't know, maybe green. Yeah, here's green. Alright, so and then if the robot looks this direction, right? What are we predicting that the robot should see, right? So here's like the image. The robot should see something like P1 over here, something like this. P2 over here, and then P3 over here, something like that, right? More or less. Yeah, all right. And then let's break down the process. So we have the following. We have pose of the points 1, 2, 3 in the word frame. We have also the pose of the camera in word frame, and then let's break down the process into steps. So first we have situation in word frame. This is exactly as we have drawn over there above. So this is a word frame, and then we're going to bring this into camera frame, where the orientation of the coordinates x, y, z is exactly the same, but the center of the word is in camera. So something like this. So here's the situation. The camera is right here, right in the middle of the beginning of the coordinate system, and then the triangle is somewhere around here. So this is camera frame, this is words. And then we're going to bring this into, so remember how the picture, right? It's coordinate system starts, or like is defined in a way that like x goes right in the camera. So looking from the sort of first person perspective, the x goes to the right and then y goes to the left. So now we will need to go into this flip word. So let's call it flip. Could also like call it image maybe. So it's going to be like this. It's going to be more or less, so the beginning of the coordinate system is going to be the same as in the camera frame, but the axes are going to be different. So this has to go right, this will be x, and then y goes down, because like again, like how I remember, it's like 640 by 480, right? So this is the longer, so this is the first one, and the shorter is the second one, 480. And the z goes out of the camera, so here, and here's our triangle, something like this. And then in the, and this will be more or less our picture. No, wait, I draw it incorrectly. Like, just keeping the perspective, it will be something like this. Yeah, it's z equals 1. So yeah, this is even incorrect, right? Because like the triangle is at like z equals 5 more or less, plus minus. So z equals 1 is somewhere around here, and then the camera just sees this, and we're going to compute those intersections, and then yeah, like here and here, right? That will be like a picture of our triangle more or less. And then finally, so in this image frame, right, like if we would redraw the z equals 1, so the middle of the z is so this thing, right? Wow, that's so hard to see. Like this thing over here. So the axis, OZ axis, it goes right here, right? And this is like the optic center, right? And like yeah, our triangle will be somewhere here, right? And then we need to go from this image, or like flip frame, to 2D. So this is sort of like 2.5D, right? Because like everything is reprojected into z equals 1. We're going to have to redefine this axis such that it doesn't start here, but it starts in normal like image coordinates, like this, right? So x goes here and y goes here. So the axes are sort of in the right places, but where the image begins is not like right in the middle, but like on the side, and then the unit of measurement is pixel. So we'll go through this from this image to the pixel. So that's the plan roughly, and yeah, let's just work our way through one example of this. Yeah. So step one. Word to come. So, and then we will work our way through the same example in code actually. So, word to come. The pose of camera in words. Yes. As usual. And then it was what? -5. and then this, and then this rotation thing, right? It says that we're looking towards X, sort of by definition, by convention. And what we have as well is like position of point 1 inward, and that was what was it again? -2, -1. So 0, -2, -1. Right. So if we want to get this position of the point in the CAM, we need CAM word point 1. So we have this directly, right? That's this. And in order to get this, we need to invert the, so CTW is so yeah, actually we can make a so first what would we expect, right? So like if I draw a coordinate system like this, wait, that's not pretty enough. Yeah, right, like this, and here's my beginning of the coordinate system, and then I draw our camera right here, and then if I would draw another coordinate system right around here, right? So it's like if beginning of the camera coordinate system is at x equals -5, I predict, so this is in word, right? So camera in word. If I start counting from the beginning of the camera, I can see that it's like 1, 2, 3, 4, 5. The beginning of the old word coordinate system in camera, that's kind of opposite. So beginning of the word in the camera system is at x equals +5, right? So it's like 1, 2, 3, 4, 5, and then y is 0 and z is 0. So what I expect to get is that this, so word in camera is this, nothing, +5. So now let me try to invert this matrix and see if this is indeed what I get. We'll just do this on the computer. Collab. How do I say it? Like WTC, and then I can say 0 - 1 equals -5, right? And just print it, WTC. Alright, and then if I do inversion of this, what would happen? Nice. So yeah, this is exactly as we have predicted. So that's nice. So I can wait. Sorry. Yes, I can come back to this and just use this equation. So the position of the point in the camera frame is the this matrix, which is like position of the word in camera frame, sort of, right? Like we could say this like camera transformation matrix, and then or camera extrinsic matrix, and then position of the point in word. So that's all we would need. So yeah, this is our step 1. We have completed it, right? So this is good. And then now we would need to transform from the camera coordinates to the flip or image. Flip is sort of my name. I don't think that anyone else uses this name, but we need to transform to flip coordinates. So let's do this. So yeah, number 2 is from camera to flip. So, and yeah, actually let's compute this real quick in the computer, right? So where's my mouse? Yeah, here's my mouse. So word in camera is this, and then our point was I4, and then point in word, let's call it zero. What was the position of our point? It was like 0, -2, 1, -2, and then -1. Alright, so point in words is this. This looks as expected, and then like point in camera is equals to word in camera times point in word, and then point in camera is so x is 5, this is as expected, and then yz is -2, -1. So that's awesome. That's exactly as what we would expect. Right. So back to the drawing board. Okay, and going back to the camera and flip. So let's draw this again. And again, I'm just like repeating it many times so that it's easy to understand. Oh, but I'm drawing worse and worse. Let me draw again. Whoop. And then whoop. And then like this. And then again is this, and this. Alright. No, come on. Yeah. Yeah, and now let's think. So the camera is looking to the right on our image. So, and then the Z was in the image frame, in the flip frame. So this is the flip or image frame, and this is the cam frame. The Z is looking out of the camera, and then X is to the right, because like 640, the longer dimension, is to the right, and then Y is to the down. So, and then in the classic normal coordinates, it was like X, Y, Z, something like this. So, X becomes X maps to Z. Y maps to minus X. Right? So my Y is minus X. Y is minus X. And then Z maps to minus Y. So now let's like design a matrix that enables this. So here we have like X, Y, Z, and 0, right? So this is sort of the, so here we imagine like here's like probably the rotation matrix and so on, but like it's just unit, so I can ignore it. So I just take like the last column of the matrix that we're going to multiply, and then here I want to design the like here's like anything, I don't know, just one, we can put anything really, and then let's design this rotation matrix that like will align those, will flip those coordinates. So here I don't care, I'll just put 1 and then nothing. So I want x to map to z, so x has to map to z, so here this has to be 1, right, and then x maps to nothing else, so just 0 and 0, and then I want y to map to minus x, so y has to map to minus x, so here -1 and also zeros because it maps to nothing else, and then z I wanted to map it to minus y, so nothing, minus y and 0. So yeah, here's our transformation matrix, right? And then like if I want to say, okay, what's the position of the point in the image frame, right? So it has to be like image in camera, just looking purely at like, you know, mechanics of how it works, and then the position of the point in the camera. So we have this from the previous step, and this is something that we have just designed, right, to make it specifically in this way. So it's kind of nice because like we can, this mechanics of the notation force us to understand what's the position of the camera in the image, although it's kind of like this not really intuitive, like a flip, right? So we write something out, we design it to work in a way that satisfies our constraints, and then only after this, from theory, we sort of understand what it really is. So that's nice. So we can say, okay, so in code it will be like camera in image, in image frame, and yeah, of course I should write it. If I were really careful about notation, I would say in image frame, but yeah, I just make the variable names a little bit shorter. So let's just transform this to the code. So okay, -1 at this position, -1 at this position, and 1 at this position. Camera and in image. Camera in image equals np array, and it was like, just do a bunch of zeros. It was -1, -1 and 1. That's, and yeah, we need this 1 at the end, like this, and like this. Perfect. To camera at image, and then we can say, okay, camera in image, and then we can say point in image equals camera in image times point in camera. Awesome. So now let's think if this is what we would expect. 215. Let's go back to the our drawing. So we got 215, and our point was like 5 minus 2 minus 1, if I remember correctly. Yeah, -2 minus 1. So it was like 5 here, and then -1, 2, and then -1 here, and then let's see, we got 215. So let's see if it worked like this way. So it's like 1, 2, and then 1, and then go this direction 5. So yeah, it looks like it worked. It looks like it's exactly the point that we were expecting. So this completes the second translation, right? So, or sorry, second transform, right? So we went from word to camera, and then we went to flip. And now we want to do this final point. So we want to project it to z equals 1, and then we want it to we want to go to the pixel frame. So let's see. So now we have a point that's like 2, 1, 5, and we want to project this point to z equals 1. So how do we do this? So turns out we can just literally divide by the z. So if, oh come on, what is this? So if I have points x equals 2, y equals 1, and z equals 5, I just want to make it, I just, so like the coordinate frame looks something like this, right? And like here's a point, and then here's like a line, and I want to evaluate this line as z equals 1, and like just purely, so there's no like intercept or anything like this. So all I need to do is I just need to divide by current value of z, and I will get exactly the point on this line. So it's like a small maybe exercise to the listener if it's not obvious for you, but yeah, this is pretty much how it works out. So sort of, yeah, maybe I can call it x normalized, or like we could call it x image. So we have 2 over 5, and then we have 1 over 5, and then we have z equals 1, and this will be our this is where our point will land in the image. So here's our image. Yeah, it's somewhat arbitrary where our image ends and where our image begins. So yeah, I don't know, I can choose like minus 1.5 and 1.5, and then I don't know, like 1, sorry, minus 1 and 1, and then this point in the image would be something like, so x goes to the right, like 2/5. So if 1 is here, I don't know, 2/5 is here. Oh, wait, I drew this incorrectly, right? It goes down. So like here or something, and then 1/5 down, like here. Let's say, right? This would be our point. And this is all like in image frame. And this is exactly where we lose the one dimension, right? So we went from 3D by projective geometry to 2D, right? We have just like flattened it. And here we need to be careful about depths and whatnot, but yeah, all of this will come. So we have the final step, right? We have the point in the image coordinates, right? And the image coordinates look something like this. Opa. 1.5, and then minus 1.5, and then I don't know, minus 1, 1, and we have our, so we have our point over here somewhere. And then we want to go to the pixel coordinates, where that begin 0, 0, and then go to 640 by 480 or any other arbitrary resolution, right? So let's just try to figure out what's the mapping. So the mapping is, it seems that the mapping is linear in dimensions, right? So it just like uniformly linearly scales the axis with some shift, right? Just we need to squish and or expand and shift. So let's see. So we want -1 to map. So this is like minus 1.5 actually, minus 1.5. We want this to map to 0. And then, yeah, so, yeah, actually it will be something like this. So, x pixel will be equals to like some scaling factor times normal x plus some constant that shifts the center, right? So let's look at it now. So we want 1 minus 1.5 to be mapped to 0, and then we want 0 to be mapped to like, so this has to go here, so to like half of the 640. Half of 640 is 320, and this is already enough. So because like if we put 0 here, then it implies that the cx has to be, so this has to be 320, and then from this we can figure out what's the f of x. So if 0 equals f of x, which is what we want to solve for, times minus 1.5 plus 320, what this implies is that f of x has to be 320 over 1.5, something like this, right? And then in the same way we could try to figure out what's the f of y. So what's that, like half of 480 is 240, and then over 1. So here's our f of y, right? Nice. So yeah, and this is something that's so vector. So yeah, basically we can write this like this. We can write this like this. So xp and yp is, so it's commonly written out in this form, is fx nothing fy nothing 1 cx cp cy, and then times x y z, and z is sort of assumed to be it's assumed to be 1, or you could say it's sometimes also written in this way, like you divide everything by z, so you do like 1 over z, and then yeah, that's like a way to write it. And this is often called camera intrinsics matrix. So camera intrinsics matrix, and then the pose of the the pose of the camera in the word frame, it's often, and sometimes also together with this flip, sometimes not really. So yeah, basically the flip can belong to intrinsics, so the things that are internal to camera, and then the position of the camera, it's sometimes called the extrinsics matrix. So this thing over here, right? It could be, it's sometimes called extrinsics matrix. Alright, so now let's move this to code. So where's my mouse? Here's my mouse. So we stopped at point in image, and now from the image frame we want to go to normalize the z. So we can do point in image translation only, so like we don't really care about the rotations and so on, right? So we do point in image like this. Yeah, and then point in image plane, it will be something like this normalized. Yeah, it as well. Yeah, nice. So 0.00402, so 04 to the right, 02 to the down. And now we can define our like f of x and whatnot, and just like transform it to the final pixel. So I don't know, image plane. So how would it be? Like we need like image plane in pixel. In pixel is something like, so f of x, it was 320 by 1.5. F y, it was 240, and then cx was 320, and then cy was 240, and then this was or also called camera intrinsics matrix. It was so f of x, fy, cx, cy, and y, and let me call it d-type equals float 64. Let's see. Oh, we dropped a bit. Okay, and then we can do image, or like point in pixels. Point in pixels. All right. So our point in pixels is like 405 to 88. And that's how you render actually. So you take a triangle, you make all those transformations, and like, by the way, we could just like reproduce all of this by just stacking all those transformations at once. So let's do exactly this. Word in camera. Point in image. Oh no, but you need to divide, right? So there we won't be able to make like a nice chain of linear operations, because here's our like projective non-linear operation. I think there maybe there's a way to actually express it as some kind of like matrix multiplication, but I forgot right now. But yeah, basically this is what you do in rendering. So let me show you what I mean by this exactly. So what you do often, or like how the computer rendering works, right? So like you have some kind of object, I don't know, like a hero in a game, the Witcher, and then you express the Witcher as sum of tiny triangles, right? So like let's say you have a ball, right? And then you just like divide this ball into a series of triangles. So like, yeah, triangle. So you have like a bunch of these really tiny triangles, and then in parallel for all of them at once you take this and this and this, you transform it to, so you know what's where the Witcher is in the word, you transform from the words to camera, from camera to image, you project it to the image, to z equals 1 in plane, and then to pixel frame, and this is exactly what you show to the user, right? This is how rendering works. And like the modern graphical cards, just you do all of this really fast in parallel. So you have like huge parallelism, I don't know, like you can do this for tens of thousands of triangles at the same time. So yeah, that's more or less how rendering works. And like rendering, you could say, is like inverse problem of the visual mapping, because if you can figure out what the robot should see, you can compare it to what the robot actually sees, and then you can based on if you can track identity of objects or like of the points in the image, you can figure out what's the movement of the robot, what kind of movement of the robot this implies. So yeah, in the next lecture we are going to probably in less detail go through like a simple rendering framework and render a bunch of things, and then start working our way backwards. So figuring out a way how to infer motion of the robot from the tracking of the points. Cool.